Hi, and welcome to the Media Roundtable, Borehole Observation Networks, taking the pulse of earthquake generating faults. I'm Hope from the Media Relations team. I think introduced to everyone so far. Just a quick note at the top about the format of this. In person, usually these are held around a table. So the tone is meant to be informal, kind of an open discussion between the journalists and our panelists. The scientists here today will briefly present some materials, and then you are all free to ask questions on site. If any of you are on site, I don't think anyone is, but Demian here is on site today. Slides and additional materials will be posted to our press information exchange on AGU Connect. We'll drop a link there shortly. The recording of this video will also be posted to AGU's YouTube channel, and we'll drop a link to that as well. If Zoom goes down for any reason, we will switch over to our teleconference line. If that does happen, I'll immediately send out an email to all of you, pointing you to where to dial in. So look out for that. If there are any technical issues during this roundtable, feel free to email news@agu.org or simply drop a note into the chat and we'll be happy to help you. Just to reiterate, it's supposed to be an informal, open dialogue. So feel free to ask questions whenever. I'll now turn it over to Constantino from UT Austin to introduce the panelists and kick us off.
Thank you, Hope. And thank you everyone for being here. Let me just share my screen 1 second. Oops. Okay, so as Hope said, my name is Constantino. I'm the communication specialist for the University of Texas Institute for Geophysics, or UTIG. We'll be giving you a short presentation today about a new network of borehole observatories that are monitoring earthquakes off the coast of New Zealand and Japan. And just to give you a very tiny bit of background about these, the actual technology behind the borehole sensors has been around since the 1990s, but we're using them in new ways to wire up earthquake faults and track movements in minute details. The specific earthquakes that we're focusing on, I'm sure you're all aware, are subduction zone earthquakes, and these are the world's largest earthquakes and generate tsunamis that can threaten coastal communities hundreds of miles away. And so where do borehole observatories fit into all this? Well, that's what Laura and Demian will be answering. Let me just introduce them quickly. Demian is director of UTIG and professor at UT Austin's Jackson School of Geosciences. He studies the processes behind large earthquakes and tsunamis, and he has been co-chief scientist on 5 major drilling expeditions with the International Ocean Discovery Program. Laura Wallace is a research scientist at UTIG and also has a joint position with GNS Science in New Zealand, where much of her research is used to inform earthquake and tsunami hazards. She was also the first to record slow earthquakes, or slow slip events, which you'll be hearing about later. That was at New Zealand's Hikarangi subduction zone. And like Demian, Laura has led expeditions and cruises to monitor and study subduction zones with the IODP and other ocean science missions. Demian and Laura will end there. When we end our introduction, we'll be showing a short preview of a film all about the research. It's called In the Subduction Zone. And then after that, we'll open the floor to questions and discussion. So to get things started, Laura, could you tell us, why are subduction zone earthquakes so dangerous and what are we doing about them? Oh, we can't hear you.
Thanks, Constantino. This crowd is pretty savvy to subduction zones. Most of you have talked to Demian and I about this sort of thing before, so hopefully this isn't too remedial for you. But we're talking, of course, about earthquakes generated at subduction zones, and of course, as most of you guys know, subduction zones are where one tectonic plate sort of dives down, or what we call subducts beneath another. Constantino, can you go back? Thanks. And a lot of that is occurring around the Pacific Rim region. The Pacific Rim is really ringed by, the world's largest subduction zones, and these subduction zones, because the plate boundary faults, that are at subduction zones are so large, these subduction zones host 90% of the world's earthquakes in terms of global kind of earthquake energy release. And because so many of them are underneath the oceans, and movement along faults, along the subduction zone faults in an earthquakes can, in a subduction earthquake can cause large displacement of the seabed. And that's what generates large tsunamis in many of these subduction zone earthquakes. And it's really the biggest, risk in terms of earthquakes, in terms of loss of life. It's the tsunamis that can get generated by subduction zones. For example, the Indian Ocean earthquake in 2004, the magnitude 9.1 that, thousands of people. And likewise, the magnitude 9 earthquake in Japan, which was also quite devastating. As you can see from this map, a lot of the world's subduction zones are largely under the ocean. So this presents a lot of challenges to actually being able to monitor and sort of keep our finger on the pulse of what's going on with these subduction zones, because most of the sort of traditional monitoring methods with seismic networks and networks of GPS instruments, that's largely, done on land, and it's much more difficult to do comparable types of sensing in the offshore region. Okay, Constantino, next slide, please. So this is just showing sort of a cartoon type image of what a subduction zone looks like. Particularly, this is sort of focused on the Hikarangi subduction zone in New Zealand, where we have the Pacific plate subducting beneath the east coast of the North Island. And the two plates are coming together along a feature that we call the Hikarangi Trough. And that's basically the trench, and that's basically where the plate boundary surface is at the seafloor. So the subduction zone in New Zealand is probably, we think, poses probably the largest seismic and tsunami hazard to the New Zealand region. And one of the other interesting things that we've been spending a lot of time studying, both in the subduction zone in New Zealand and also lots of subduction zones elsewhere, is this phenomena called slow slip events. And a slow slip event, what that is, it's basically an earthquake in slow motion. It involves more rapid than normal movement between two pieces of the Earth's crust, in terms of slow slip events lasting potentially days to years, whereas in an earthquake, that movement between the two pieces of the Earth's crust can happen suddenly in seconds. So you get that sudden energy release and the seismic shaking. These slow motion earthquakes or slow slip events have really only been recognized as being kind of a very widespread phenomenon, particularly at subduction zones over the last 20 years or so. And one of the reasons that they're really important to understand is that there have been a couple of cases like the magnitude 9 earthquake in Japan in 2011 and also an earthquake in Chile in 2014, where there's good evidence that a slow slip event actually occurred before those large earthquakes and may have actually triggered those earthquakes. So there's a real pressing need for scientists to try and understand what this relationship is between these slow motion earthquakes and the sort of more normal fast slip earthquakes that we tend to think of, and really try and figure out if we can understand that relationship between these two different types of slip phenomena, could we actually use slow slip events to actually do a better job forecasting earthquakes in the future, and better quantifying the likelihood of earthquakes sort of over the near term when a slow slip event is happening. I don't think we'll ever be able to predict earthquakes. I think that's going to be very much probably impossible, but doing a better job forecasting is certainly, I think, on the horizon. So this is one of the reasons, of many reasons, why we study slow slip events. So now I want to turn it over to Demian to talk about observatories.
Thanks, Laura. So Constantino, can you advance to the next slide? Yeah, okay, great. So yeah, one of the key objectives of monitoring offshore is to be able to monitor and really kind of triangulate on the position of anything that's moving, kind of what we call the creaks and groans of the plate boundary. And so in this image, it's kind of, you're seeing the seafloor. So everything that's blue is off the coast and it turns green at the beach. And it's kind of a perspective image that's exaggerated in the topography a little bit. And then the cutaway shows you, oh, can you go back there, Constantino? The cutaway shows essentially an ultrasound image of the subsurface and the plate boundary that forms the boundary where earthquakes would localize and slip or move between the subducting plate and the overriding plate is shown with those black arrows in the blue. And so as an example, this is from offshore Japan. one of the things that we've done to monitor these systems is to drill boreholes below the seabed. So this is in anywhere from 2 kilometers to near 4 kilometers of ocean depth, and then drilling into the subsurface from the ocean floor downward another several hundred meters, where we can embed or entomb sensors into the rock formation. And this does a couple of things for us. First of all, it gets us away from noise, much like it is done on land when possible to bury instruments so that you get away from surface noise from ocean currents and other things. And then also it's more strongly coupled to the rock itself. And so it's much more sensitive as an indicator of things moving. And so before moving on, just to give you a sense for what this means, you could imagine being in Poughkeepsie, New York, and trying to monitor something at the bottom of the Empire State Building with sensors that are at the top of the Empire State Building, and to be able to see something moving a few millimeters over the course of a week or so. And that's really what we're able to do with these sensors. It's actually extraordinary in terms of the sensitivity that we're able to achieve. So this allows us to monitor tectonic motions, both in a place that's really critical and at a precision that's unprecedented. I think now we go to the next slide. It's just to get a sense for what these things look like. They're actually large pieces of instrumentation. So these are installed by drilling. And so that's kind of shown a couple of images, with people for scale showing just the top part of these systems. And so this is the part that's installed with the communications and the electronics in it that's actually sending information either back to shore or storing it in essentially a memory bank at the seabed, and then we plug into that. And I think we can go to the next slide as just kind of move along. And so again, just to get a sense for the scale of these things, so this is now, actually on the left-hand side is a photo of Laura, along with 2 other colleagues, for one of these systems that was being installed off Japan. And what you see there is what we call the wellhead. So this is kind of the business end of this system. So you drill the hole, you install the sensors down at the bottom of the hole, and then there are cables and hydraulic pipes, narrow gauge pipes that bring the signals back up to the sea floor, a few hundred meters to maybe a kilometer above that. And then nestled at the sea floor is this set of the electronics and the relays and the valving. And that's what you see here is the actual, again, that sort of critical link, or what we call the wellhead. And so they're quite photogenic, especially if you spent a lot of time with them like I have. And this is what they look like. And again, these are pretty, these are 10 meters high, just this top part. And this is where we plug in to connect to a fiber optic network, for example, in Japan, that's sharing signals in real time back to shore. And on the right is just a view from above as one of these has been lowered in. It's just, again, sorry, Constantino, go right ahead. That's just with that right hand photo. And so just to give you a kind of a snapshot of the kinds of things that we're observing with these systems and why they're so key. This is a figure, just a simple example showing the response of 2 boreholes at different locations and their responses to one of these slow slip events back in 2015. And this is work that was presented at this meeting where we've analyzed this event in a lot of detail. And the vertical scale here is the pressure change down in the earth, in the bottom of the borehole, as a function of time. And the amount of time that's shown here is about 3 months. And so hopefully everybody can see the blue curve is sort of flat and then it drops down. And that's at one particular location, we're actually seeing that slow event is causing extension of the rock. It's actually decreasing the pressure, decreasing the stress at that location. And at the same time that that's happening, the red one is actually being squeezed and the pressure is going up. So this is an event where we're actually tracking the squeezing or extension of the rock in the subsurface with a resolution of a few tens of parts per billion, which corresponds to about a centimeter of motion on the plate interface, the boundary between the tectonic plates, a few kilometers beneath. And in this particular case, what we've actually been able to resolve is that this is a case where we believe that slow event is kind of unzipping from some deeper location all the way out to the trench, the very shallowest end of the system. And as Laura has alluded to, this is, again, kind of a key area in understanding whether strain is accumulating there or whether the stresses are being relieved in these slow events on some regular basis, and how much is really essential for how we understand and think about the hazards in these systems, and particularly for tsunami hazard. I think that is it for me. Laura, Oh, and then this just quickly illustrates, these little dots here are in map view now, a swarm of tremors that actually accompanied that event that I just showed you the records for. And so it's just additional sort of corroborating evidence that it does look like this particular event kind of unzipped and went not just to some shallow depth, but really all the way out to the very tip of the system, that area farthest from land, where it's most difficult to sense otherwise. I keep thinking I don't have any more slides. All right, so this is the last one. And so one of the other things that these systems enable us to do is actually to establish a kind of catalog, if you want to think of it that way. And so what's shown here is just a recurrence. And New Zealand has an even more regular and more spectacular record of this kind of regularity or recurrence of these events. And this is essential as well, because what it tells us is it's not just every once in a while one of these small events, these slow events happens and relieves some amount of stress, but actually they're quite regular. So in this case, it's roughly every 9 to 15 months. And if you were to add up how much motion these accommodate, it's a significant fraction of what otherwise we might have thought was being built up in between large earthquakes every decade, every 5 to 10 decades, 50 to 100 years. So again, sort of a significant advance in our understanding of how this outermost kind of essential part of the system is behaving. Laura.
Hey, so I guess I'll talk about the what we've done in terms of similar types of borehole sensors to what Demian was talking about that have been deployed at the offshore Japan. We've done similar types of things in New Zealand in the last few years. In 2018, we installed 2 of these downhole borehole observatories offshore the east coast of New Zealand. So this map, the map up on the right there, that kind of gives you a broader New Zealand view. That's focused on the North Island here. You can see that white square there. That's what this blown up map is. And this is off what we call the northern part of the Hikarangi subduction zone. And this is a part of the Hikarangi subduction zone where we've seen with previous both seafloor instrument deployments and also onshore networks of GPS stations that are recording the movement of the land in these slow slip events, is an area where we see very large slow slip events and quite frequent slow slip events. The black contours on that map are showing the location on the subduction zone where large slow slip was detected from a network of onshore and offshore sensors in 2014. And those numbers there are in millimeters. So we're looking at up to sort of 15 to 20 centimeters of movement along the plate boundary during that 2014 slow slip event. So this area was targeted. We targeted this with our observatory installation because we see such large slow slip events here and quite frequently and very, very shallow. So we were able to put observatories in very, very close to where the action's happening, to where the slow slip is happening. As Demian termed it, being able to really see the creaks and groans very close to these events is going to give us a lot of insight into the processes that happen during these events. And going for these very shallow slow slip events at offshore subduction zones, that's really the way to get up, really up close and personal with what's happening in these things. This area has also been the site in 1947, the blue star on that map close to one of our observatory sites, U1518. That was the site of an earthquake in 1947 on the subduction plate boundary that actually caused quite large tsunami, about 8 to 10 meter tsunami in 1947. So these slow slip events are also occurring in an area where earthquakes that do generate tsunami occur. So our 2 observatories in New Zealand, one right out near the trench, site U1518, that's goes through an active fault that sort of splays off of the subduction zone, and then site U1519 closer to the land. And that's above a really large area of movement on the subduction zone during these slow slip events. Constantino, can you go to the next slide, please? Thank you. And this is just showing some of the data that we've obtained from the observatories. We were able to go out and I'll show some pictures of that later, but we were able to go out with a remotely operated vehicle, ROPOS from Canada, to basically plug into the observatories that we installed in 2018 and download the data. And this is similar types of things to what Demian was showing from the Nankai Trough. And this is showing the downhole pressure changes that we recorded. And if you remember from what Demian said, an increase in pressure means that there's been contraction in the borehole, and a decrease in pressure, sort of downward movement of those black lines, means that it's been extending or expanding. So the top record is from our site that's out very, very close to the trench. The bottom record is from the observatory closer to shore, above the really large slow slip patch. And then the red time series is showing a time series of position from a continuously operating GNSS site, or a lot of you think of it as GPS. So it's basically a permanent site on land, operated by GeoNet in New Zealand, where we can continuously track the position of that site, you know, at a kind of millimeter level every single day. So traditionally, onshore GPS sites are the way that people have been able to detect and track these slow slip events at most subduction zones. For example, when they were first discovered by scientists in Canada and Cascadia, it was onshore GPS networks that showed them they were happening. And so this is what we've mostly been using in New Zealand, but now having these offshore borehole observatories that we've installed gives us a whole new view on it, much closer to where that action is happening, much closer to where these slow slip events are happening. And one of the other things I really want to point out is you see the GPS time series in red. It's quite noisy, really, compared to the black time series from the observatory data. So it's really demonstrating how much more sort of high fidelity view we're getting of what's happening during these slow motion earthquakes in the offshore region. And that's really exciting, because one of the big challenges for measuring these types of things offshore is there's a lot of sources of noise from oceanography and things like that, making it very, very difficult to get a clear view of what's going on. But these downhole observatories really change that. They're really giving us a very clear picture of what's happening. So I'll just focus in on a few features. You can see in the red from the onshore GPS, this big upward jump. That's a 4-centimeter eastward displacement in March and April of 2019. And that was a large slow slip event that happened right beneath our observatory network. And you can see this pressure increase at U1519 really tracks that almost exactly. This is the site that's closest to land. So it's seeing very similar things to what the onshore network is seeing. However, there's a lot of differences when we get out to the trench. The onset of contraction is later at the site out near the trench. And it looks like the slow slip event persists for much longer, and it may even go into a more of an extensional phase later, which could suggest migration of the slow slip right out to the seabed, right out to the trench. And then we also see in the U1518 record, lots of these little blips. Some of these we see at the same times that we see evidence for slow slip events on the onshore GPS, but other times we don't. And so this is really suggesting that perhaps there's lots of little slow slip events happening right out near the trench that are too far offshore and too small to actually see with the onshore networks. So this is really, I think, opening our eyes to the whole range of things that are happening on the offshore Hikarangi subduction zone in a way that we've never had been able to do before, because we just haven't had that capability to see what's going on in a very similar way to which Demian and others have been able to utilize the borehole network off Nankai. You know, their work on that really demonstrated for the first time that there were slow slip events on the offshore Nankai subduction zone. So if we can go to the next slide, please. And then to this just very quickly, I don't want to go into this too long, in too much detail, but this is just a model, sort of a cross-sectional model of where we think the slow slip happened in the 2019 event. And we think that it happened in sort of 3 phases. You know, one phase which involved movement on the subduction zone from about 15 kilometers depth, probably all the way to the trench, and then a prolonged period of movement on the subduction zone on the further offshore parts of the plate boundary, sort of 8 kilometers and shallower, and maybe even a last gasp, this phase 3 in orange here, of a few centimeters of slip that even persisted several weeks longer than what we can see with the onshore GNSS stations. So this has really given us a whole new view into what's going on in these events that we really couldn't get in any other way. So next, I think, next slide, Constantino. This is just a picture from our recent visit in March of this year with Ropos. This is Ropos doing some valve checks at the observatory right out near the trench, that one that's the furthest offshore. So this is what the wellhead basically looks like, where we where we go and visit and we go and download the data. And that's just a picture of Ropos on the left. We actually deployed Ropos on New Zealand's research vessel, the Tongaroa. And it was the first time that the Tongaroa had deployed an ROV like that. So it was really exciting that it worked really, really well. Next slide. And I think we're going to wrap up with a trailer from Magnolia Low, a documentary filmmaker in New Zealand, joined us on one of our Tongaroa research voyages, and to try and document some of the work that we're doing, trying to understand what's happening on the offshore Hikarangi subduction zone. So, and yeah, Veronica was there for a lot of this with us as well. So this will look familiar to her. Oh, she's not here anymore. So anyways, Constantino, do you want to play the video?
Yeah, give me 1 second. I'll get it going. Video. There we go. So I'll start this off, and if the sound's not coming through, if it's all choppy, then stop me, and I'll do it again. And I've seen that Veronica's just popped up again, so we're all here.
My major research focus, really particularly over the last 10 years, has been on this thing called the Hikarangi subduction zone. And it's New Zealand's largest plate boundary fault. And it's where the Pacific and the Australian plates meet offshore the east coast of New Zealand. And it's our largest fault, and it's our fastest moving and most active fault. And it arguably poses the biggest seismic and tsunami hazard to New Zealand. Over the last several years, it's become really apparent that the big part of it that we need to understand is the offshore part, because that's the part of the subduction zone, you know, where a lot of the earthquake activity is going to happen, and also where tsunamis can be generated. And that's the part that poses the biggest hazard to New Zealand in terms of potential for loss of life. One of the big things that we're going to be doing over the next few weeks is we're waiting for a really big underwater remotely operated vehicle. This particular one is coming from Canada, and his name is Ropos. This is really exciting. This is Ropos. I'm going to shake his hand for the first time. Ropos, it's really nice to meet you. Getting this voyage going and sort of sorting out logistics, making sure that Ropos could be deployed from Tongaroa, because Tongaroa hasn't deployed a remotely operated vehicle like this before. And just getting it into the country, getting the people into the country. It's been probably the biggest cause of stress for me over the last year, is worrying about how if this was going to work out or not. On Friday, early morning Friday, there were 3 earthquakes that occurred. One of them up near the area that we're headed with Ropos. It does have some really interesting implications for this mission that we're about to go on the Hikarangi subduction zone. What we're going to be doing with Ropos is we're going to be sending Ropos down to visit these observatories that penetrate about 400 meters below the seafloor. And so they're measuring all kinds of different changes in the Earth's crust. So we're on our way down to the first quark site that we're going to visit, the first subseafloor observatory. I'm successful in 19200 baud! Woohoo! Jesus. Did she get her God? 10 years of work, and we're finally getting this data. So what happens from here? I'm going to take the weekend off and recover from what has been kind of an intense last year of planning, getting this voyage, you know, to happen, and really want to dig into the data a lot more.
Cool. Thank you, Laura and Demian. Have we? Yes, Laura's still here. Let me just get this up again. So yeah, so now's the part where we open the floor to questions, and you can raise your hand. Alex, I see you've got a hand up. Do you want to ask?
I do. Yeah, I'm sorry. I'm going to have to bail off for an unavoidable appointment pretty soon, but thank you both for the update. Laura, I just wanted to ask you to maybe talk a little bit about how applicable the lessons from the Hikarangi subduction zone are to other parts of the world. So it's really interesting that you're finding that these slow slip events last longer than we would know from onshore. So not only is slow slip happening, it's happening longer. But how applicable are these lessons from subduction zone to subduction zone?
Yeah, I think that's a great question. And I think one of the, I guess, what I would focus on for that quite a lot is that, you know, there is evidence from other subduction zones also have these shallow slow slip events and shallow slow motion earthquakes, like offshore Ecuador. And I would imagine lots of subduction zones that are actually submerged beneath the ocean, where we don't even have a capability with GPS or anything to see that they're happening, that they're probably happening there. So I think the number one that this work is giving us really the first insight into what these slow slip events are doing on the shallow offshore parts of the plate boundary, particularly in the Hikarangi case, where we have these really large ones, and also in areas where we've previously had tsunami-genic earthquakes as well. And I think that the work on Hikarangi is also showing, you know, we have this kind of co-location of where the tsunami earthquakes happened in 1947 and where these slow slip events are happening. I think this is also telling us that, you know, just because they're slipping in slow slip events doesn't mean that they also can't slip in earthquakes and generate tsunami. And I think that's been kind of a common assumption about slow slip events. And Demian may want to make some similar comments as well about the Nankai experience. And then as I mentioned before too, the site out near the trench that's furthest from shore, it's not only suggesting the slow slip's longer, but we may actually be having lots of small ones in between, not just the big ones that we can see on shore with the GPS, but there may be lots of little ones happening out there as well, that we had no idea were going on before. And that's probably, I mean, Demian may want to make some comments about that, but that's probably related, you know, potentially to some differences in frictional properties of the rocks out there and fluid pressure versus a little deeper down. I don't know, Demian, do you want to say anything more about that?
I would echo a lot of what you said, Laura. I mean, I think what we've learned, another thing we've learned is that monitoring at the most distal site for both Hikarangi and Japan is really essential. I mean, that's been, you know, without that, it's still, the precision is still unbelievable, and we're seeing things we would never, that are invisible on land. But having that observation way out at the outer part of the system is really telling us how the area where the seafloor might be uplifted in the tsunami-genic event, how is that area behaving? And without that, as Laura, I think you termed it the blind spot. And that's something that's, I think, universal to subduction zones, is we have very little information. So the applicability is really huge. I mean, every subduction zone in the world should have these kinds of instruments if we really want to understand. And I'll just add, you know, it is true that areas that are hosting these slow events can still kind of be kicked from behind and participate in the large earthquake. But if they're relieving stress and strain by the slow events, then the picture's very different, and the physics is very different, because it means that they're less likely to be contributing energy to those events. They can still participate in them. So it does change the hazard outlook significantly, and I think that's pretty universal, a sort of a global application.
And one of the other things too, that in the Nankai case, as Demian mentioned, they have a seafloor network as well of seismometers. And in New Zealand, we also had an ocean bottom seismometers deployed during the 2019 slow slip event. And we've also got some temporary seismometers up there right now. And so having these co-located observations from the ocean bottom seismometers to get a really fine view of the earthquakes that are actually happening out there during the slow events as well. And then linking that up with what we're learning about where the slow slip events are happening and how large they are, is going to really help us go a long way towards understanding this relationship that I mentioned earlier between slow slip events and earthquakes. You know, how much do slow slip events increase seismicity rates on subduction zones? And that's a critical question that we need to answer if we're going to be able to ever use these slow slip events to help do better forecasts of earthquakes. We won't be able to predict them, but we may be able to do a better job forecasting them. Maybe not as good as the weather guys do, but but that's the other critical piece of information there, is having these co-located sensing capabilities.
Okay, great, thanks, and sorry to drop off.
Richard, go ahead.
Okay, if I had to find the mute button. Yeah, I've got a couple of questions on that. First of all, I know what you mean, but I'd love a quote on what is the difference between prediction and forecasting.
Prediction is basically, you know, if somebody says there's going to be a magnitude 6 earthquake in X days, you know, maybe at X time, that's, you know, or there's going to be a magnitude 6 or greater earthquake this week. You know, it's a much more, I guess, a prediction would be where someone would be more confident about what they're saying. A forecast would be really incorporating the uncertainty that we have about these things, and the fact that we don't know, you know, if you know, these earthquakes are going to happen. You know, it's assigning a kind of a likelihood, say a 30% chance in the next 6 months of a magnitude 6 or larger earthquake. So that's a more realistic, forecasting is a more realistic thing in kind of the earthquake space than actually predicting one. Demian, do you have some other comments on that?
I mean, it's a little bit of semantics, I suppose, that forecasting is a subset of predicting, but it's maybe more of a probabilistic and longer term viewpoint. Whereas, yeah, I think we in our community think of prediction as the short term kind of, again, the way you think of a weather prediction, it'll be sunny and 78 degrees today. And the forecast is that an area is at increased risk or is likely to fail in an earthquake in the next 40 years, whereas the adjacent area may not.
Yeah, thanks. That's what I was like wanting you to say, not me to put it in your voices. I now have a technical question, if I can ask a second one. How do you convert pressure into movement? Because that's what you're measuring, right? Pressure change?
Outstanding question, yeah. So, and Laura should jump in here as well. So the pressure is the pressure of that we're measuring is actually the pressure of the fluids that are in the space between grains in the rock. And so you can think of the rock as like a sponge, except sort of stiffer. And so what we're actually measuring is whether the rock is being strained or deformed. So if you increase the stress on a sponge and squeeze the sponge, then the pressure will go up. And if you pull the sponge apart, then the pressure will go down. And so there's a conversion that we do that's sort of whether it's positive or negative, but then if you know what the rock's properties are, you can actually calibrate that so that a certain amount of pressure change corresponds to a certain quantified amount of strain. And so that's how we do it.
But how do you go from strain to movement?
So for that, we use models of the fault movement in the subsurface. And so when a fault moves in the subsurface, there's some region on the megathrust on the fault that would move, and that corresponds to the entire rock mass deforming in some manner, and that's something we calculate. And that's actually essentially the same technique that all geodesists use when they use what they measure on the Earth's surface for GPS movements to turn that into, or to estimate what that means for the movement on the San Andreas fault or a subduction zone fault or anything. It's a similar technique.
Nidhi's got a question in the chat. Do you want to unmute and ask it, or do you want me to do it quickly?
I don't mind. There was a leaf blower that started up just a minute ago, so I apologize outside my window. Yeah, my question was, I just wondered how the sensors in the observatories were powered? Is there a battery situation, or do they just not need power because of the way they work? Just a bit of insight would be great.
I'm just going to jump in, but again, Laura, you should jump in as well. So for the Hikarangi systems and for the systems off Japan, in their early stages in Japan, they're battery powered. However, the pressure sensors are passive. So it's essentially like a very long straw. It's a hydraulic line or a tube that goes down to the formation. So the only power that's needed is to register and record a pressure value once every minute. And so that's done at the top at that wellhead with a battery that's actually not much larger than 4 D-cell batteries. And that lasts for 10 years. Our experience is between 7 and 14 years, actually. Most recently, starting in about 6 years ago, the systems offshore Japan were plugged into a cabled network. So they're now powered with a cable that comes from on land. And the data are also streaming back in real time in that system as well.
And that would be amazing if we could get something like that for New Zealand, because in New Zealand right now, the observatories are still running on the battery power, and that'll go for quite a while, but it'd be good to power them. But the biggest benefit is actually getting that data back in real time, because then we could actually be using the information as the slow slip event's happening, as it's coming in, to try and understand what that might mean for earthquakes. And then also, yeah, there's also sensors on the wellhead at the surface, or not at the surface, but at the seabed, detecting seafloor pressure, and from that you can see things like passing tsunami and so forth. So would be a lot of benefits to getting the data in real time in New Zealand as well, and also link it in to a similar type of network like what they have in Japan with the ocean bottom seismometers and seafloor pressure sensors. So Japan's kind of led the world in their wiring up of the megathrust, and we all need to figure out how to follow, because they're kind of pushing the envelope, and it's what we really need to be doing elsewhere.
But I'll just add the power requirements. I mean, it sounds like it should maybe be a lot of power for some reason, but it's actually not. So, one borehole system off Japan that has a seismometer, one of these tilt sensors that monitors literally the tilt relative to horizontal, plus the pressure sensors and data acquisition, all of that is about 10 watt. It's sort of a low wattage light bulb kind of power for everything. And so the engineering and design that goes into keeping these sort of power lean is really impressive.
Thank you for that, and thanks for having this session.
Thanks. Maya, I see you've got your hand up.
Yeah, that actually kind of partially touched on my question, but to kind of continue on that same vein, I was curious about the data retrieval process right now for the New Zealand system, since it isn't hardwired in. How frequently, how difficult is that? And also I was kind of also curious about future plans for do you have more plans for additional observatories, either New Zealand or elsewhere?
So in terms of getting out to the New Zealand observatories to get the data out, yeah, we are dependent on being able to get a remotely operated vehicle over here. So you have to actually go and directly plug in. And we've so far been able to get one out about every 2 years, either specifically for the observatories or on the back of other experiments in the area that required an ROV. We're planning for the next mission out there is probably going to be in about a year, little over a year to a year and a half from now. To get the next set of data. So yeah, so it does make it intensive kind of planning. One of the benefits is that this last time we were able to use the New Zealand research vessel, which was really valuable because of COVID and limitations in what foreign research vessels were being able to do. That was really our only option, and we were so thankful that it worked out so well, and that opens up the possibility of using New Zealand-based platforms to be able to service the observatories. So that helps a lot. And it would be fantastic. The second part of your question, was it about kind of linking it up or linking these? Can you remind me?
I mean, yeah, I would be curious about linking future plans for linking it up, as well as plans for either additional observatories in New Zealand or elsewhere.
Yeah.
It was mentioned
Yeah.
earlier about how it would be beneficial for other places.
Yeah, I mean, we would love to be able to link these up to land, and we're definitely trying to figure out some avenues to try and help make that happen. It's a fairly big investment, but from the New Zealand side, but it would, I think, certainly be worth it. Demian, you might want to comment on other observatories. We don't have plans in the works for other ones off New Zealand, but at the moment it will be nice in the future. But Demian, you might have some.
Yeah. So certainly the Japanese research community is continuing to try to build networks there and install these same kinds of sensors in additional locations off the coast of Japan. The other two efforts that are underway that I think there may be others, but the two that I know about directly are there's a proposal to do drilling off the coast of Oregon and Washington, and that's still in the early stages. But there's a proposal in the system to do ocean drilling and to install observatories like these off of the Pacific Northwest. Part of that effort may also include trying to connect two existing observatories, which were installed in the early 1990s for other purposes, to monitor hydrologic processes, to get those connected to a network. And then there's also a proposal in very early stages in southern Japan, off of Kyushu Island. That's Laura and I are both involved in as sort of co-investigators, but that's probably in a much earlier phase. But there's certainly a lot of interest in it. It's a challenge is that it's just time and resource intensive to get a drilling ship out there for that initial investment.
Yeah, this is the best way to see what's happening on subduction zones in a lot of ways, but it's also very expensive and very involved way.
Yeah, for sure. Great. Thank you. Appreciate it.
Veronica's had her hand up for ages.
I just didn't have my electronic hand up. I've got two questions. One's really just a clarification. The difference between having a Entombed observatory and a network of seismometers, undersea seismometers on the surface, is one more valuable than the other, or do we need both ideally?
I need both.
You want me to go? I think both, in the ideal world, both is great. I mean, it depends on what you're wanting to study and investigate. In terms of things like earthquake and tsunami early warning, having the network on the seismometers and pressure sensors on the seabed, like they do in Japan, is critical for that sort of application. Getting a really good handle on what the slow motion earthquakes are doing, which also have implications for earthquake potential and potentially, helping us do a better job forecasting earthquakes. These downhole observatories are critical. And also getting at a lot of the big science questions about why slow slip events happen and what do they mean. And that's a lot of the Borehole observatory stuff comes in as well as which was
going to be my second question. If you've talked about it already a little bit when you responded to Alex's question, but I'd still like to hear from both of you anything we know about the role of those slow slip or silent earthquakes. Are they necessarily a pressure relief, or could there be a pressure buildup? How they contribute to whatever else goes on. I think it's a big fundamental question, but anything you can add to what you've already said about their role in the between the seismic and silent earthquakes, the connection there.
I would say it's both.
Two. It's a double-edged sword. Yeah. Damian,
So,
do you want to go for it?
I'll start and then so it is clear that where the slow slip is occurring in that part of the plate boundary, that part of the fault, it is relieving something that's built up. But at the same time, that means that when that moves, if there's an adjacent area that isn't participating, then that area is being stressed more by that motion. And so that's this idea that people have hypothesized or even potentially observed that the slow events may precede like a slow motion foreshock to the Tohoku-Oki earthquake, for example. So that's part of the story. But in the local areas where the slow slip has occurred, if that's big enough, then it does have significant implication for potentially reduced hazard of that area being a contributor to the energy that's released in a large event. Because by definition, if it's moved, you have released some amount of that stress. And so that, at least that's the way I think of this sort of double-edged sword, is that locally it's relieving, but it's shoving on the areas around it. And so depending on where those are and how big things are, that could have an effect down the road.
Thank you.
I guess just simple way, it's like in the long term, the slow slip events where they're happening, it reduces, the number of earthquakes you're going to have there, because that budget is lowered because things are being accommodated by the slow slip events. But it's that near term, when the slow slip event is happening, what it's doing to the faults around it. And we do see increases in seismicity rates during slow slip events. So it is clearly redistributing some of those stresses elsewhere and can change the very near term kind of likelihood of an earthquake. So it's sort of two, like Demian said, two components.
Both things, yeah. Thank you both.
Richard, I see you've got your hand up again.
Yes, I have two, again, technical questions. One is, what is the lifespan of these things? I mean, can they be, like what happens when the batteries die? You must have a way to get at them. Let's see, and what do they cost to install?
Demian, you want to go for that, don't you?
Okay, so the battery lifespans, they're designed for on order of 5 to 7 years. And part of that is it's almost entirely battery lifetime. And there's a sort of degradation because you're in cold water. And so everybody knows if you leave even your regular alkaline batteries, if you leave them out in the mud room and they get cold, they don't last as long. It's the same thing at the bottom of the ocean. So kind of 5 to 7 years is the design lifetime. But some of these systems, that's quite conservative. So some of these systems, in particular those that were initially installed to monitor mid-ocean ridges, some of the earliest generations, went for twice that long before they needed to be refurbished. And then, yes, the way that if they're not connected to a power source like a cabled network, you can go down with an ROV, and they're designed with the intent of being modular. So you can actually pull off a pressure case that contains the battery and all the instrumentation that's recording. And it's like a quick connect. You can pull that off with one of these robotic submersibles and install a new one, and it kind of fits into these. It's basically mated perfectly to just slide in and latch in. And so that's the idea, and that has been done in some of these systems. Ours are not old enough yet for that to have been a need. And I've already forgotten the other part of the question.
Installing one? The cost of installing one.
Yeah.
The cost to install one.
Oh yeah, so the cost of the actual instrumentation is actually not that high. And so for the example, the pressure sensors that we've installed, in addition to temperature sensing and a few other things, is on the order, I say not that high in sort of scientific exploration terms, about between $500,000 and $1 million for, say, a pair of these. The largest cost is really the drilling itself, because that requires ship time. And so a drilling expedition to go out there, drill the holes, put the casing to hold the boreholes open and install everything, for a 2-month expedition is on the order of $12 to $15 million US.
Thank you.
That's why we're very lucky to have these where we have them in New Zealand and Japan. It would be nice to have more of them elsewhere.
I mean, one could put that cost in perspective of the cost of damage from natural disasters, and I think that's the argument that certainly the Japanese government has considered in putting out their network.
Maya.
Yeah, thanks. So I was also kind of curious, what are the types of things that you might be able to, because there was, when you're showing those plots earlier about being able to see some of these really intricate details, it's very cool. And I'm kind of curious, and this might be a question of like, what are the results that you are having before you have them? So forgive me if it is, but I'm just kind of curious, what are the kinds of things that you would be looking for in order to understand the types of slow slip that might lead up to an earthquake versus the types of slow slip that don't. Like there have been plenty of slow slip events, and there are like the regular slow slip events up in Cascadia that we know happen regularly. There's not a problem as far as we know, or it hasn't been for decades. So like, yeah, I'm just kind of curious about what are some of those features that this might be able to reveal that we haven't seen in other types of data.
I mean, I guess Demian probably wants to take a crack at this as well. But in terms of the what kind of features of the slow slip events that we're looking for, in terms of, if there's some signature of one that could lead into a bigger earthquake, that's a huge question that we don't really know yet. And we need lots more observations, like the, ability to observe these slow slip events in the near field and be there present when that does happen, when one does lead into a bigger earthquake, to get some idea of what that sort of might look like before an earthquake. And then, yeah, Demian, do you have some other comments on that in terms of what the signature?
Yeah. I mean, I guess I don't think that it's not clear that we're seeing sort of different kinds of slow slip events necessarily, but
yeah,
I think the things we would be looking for example, are one of an unusually large size, for example,
yes,
would cause some concern, because that would, the amount by which you're stressing adjacent areas is going to scale with that. So that's important. And then having additional complementary sensors out there will allow us to see if there is tremor or microseismicity that may accompany or follow it. And so those would all be, I think, the kinds of things we would look for. And to do that, you need to know where everything's happening. It's not just enough to say, oh, something happened, but you want to be able to kind of pinpoint with some degree of precision to say, these things are related. The microseismicity began right after the slow slip event, and it happened around its edges. Something just got stressed. So that's the nature of the kinds of things that I think we would, we're kind of always keeping tuned for.
Great, thank you.
Could you elaborate a little bit on what it might take to get to that sort of position where we're forecasting earthquakes? Like what other kinds of, because we're talking about borehole observatories, we've mentioned sort of seafloor sensors, and yeah, what's it going to take to get us there?
I think I personally, well, number one, we need to have a better understanding of the process and the how these slow slip events and earthquakes interact. And one of the primary ways of doing that is just building up more information on that and building up a clearer picture and more examples, enough examples where we can say something statistically significant about, slow slip events, increasing, the rate of earthquakes by X. And we just don't have enough of that. And the only way to get that is to have permanent monitoring networks in place at subduction zones around the world to get a handle on that. So we need more data from lots more of these things. I don't think any one study in one place is going to give us the answer to that personally, but yeah.
Part of it,
or Demian, sorry.
I was just going to add to that real quick. Is that, that's actually in part some of the motivation for this new initiative that folks are trying to get off the ground. The SZ4D initiative includes many subduction zones in 4 dimensions. It includes more than just the earthquake problem, but a big part of that, and there's a town hall this evening on that here at AGU, is the idea that to be able to do anything resembling forecasting is going to require a bigger footprint of instrumentation on the seabed and to some extent in the subsurface, to be able to actually look down like in a map view and say, where is it that strain is accumulating and where is it not? And that's kind of, first order prerequisite, I think, before we can start really talking seriously about forecasting.
Cool. Veronica, I see you've got a question.
Look, it was very similar to what you just asked. I wanted to bring us back to this idea of forecasting. And Demian, it was, what you just, in response, I was thinking of the spatial distribution of what we know now and how, you might be observing a silent earthquake that releases pressure in one place, but how do you know where it builds up pressure? That's a sort of, do we have enough of those instruments out there? But could I just add a clarification more than a question? The current methods of forecasting earthquake activities rely solely on paleo data, on the knowledge we have of previous earthquakes? No?
No, there's a whole range of different things that go into those right now. And it depends on whether you're doing kind of nearer term earthquake forecasting. In that sense, usually you rely more on rates of seismicity and rates of earthquakes detected by networks. And then for the longer term hazard models, paleoseismic data, sort of evidence for past earthquakes and sort of sizes and recurrence of those is one thing. Earthquake catalogs, you know, the rate of seismicity that's been, you know, documented during instrumental periods. Long-term slip rates on faults, those are other big things. So yeah, so a lot of it's based on some of the observations of what's happened, you know, through the past. And a lot of those are limited to also land-based studies, really. It's difficult to get at some of these things in the offshore, in part due to the lack of instrumental capability to detect earthquakes. I mean, we had an ocean bottom seismometer deployment in 2014, and we saw literally thousands more earthquakes offshore New Zealand's east coast than they see with the onshore GeoNet seismic sensors. So it's, you know, getting a better, you know, and not just in terms of this types of stuff Demian and I are talking about, but getting a better picture overall what's going on in the offshore region and these potential earthquake sources is really, really critical. So yeah.
But the current modeling of hazard does not include the silent earthquake, slow slip earthquake information yet.
Yeah, well, so I think that around the world, people probably incorporate their understanding of where the slow earthquakes are happening in some cases, maybe not in every case, but where they know about them, you know, may incorporate that into their thinking about how they treat the subduction zone source and where earthquakes are likely, more likely or less likely to happen. It needs to be, I think, incorporated in a more robust way for kind of thinking about the shorter term. Like, what does it mean when we have a slow slip event? How does that change? Does that change likelihood of an earthquake in the sort of coming months? Is what I'm trying to say. Not thinking so much for the long term, but yeah.
Yeah, certainly in the long term. I mean, like at the decade scale, if something has these slow slip events, then it's not really locked up over the time scale of 10 years. And that kind of information is incorporated at least into some models.
Into some models, depending on how a different country does hazard models or a different organization does their hazard models.
But as Laura said, the short term is definitely more of a frontier, I think.
Yeah.
Cool, thank you.
I've got one last question. So how can we tag along to these scientific drilling expeditions?
You actually can. There are usually a couple of berths for outreach folks,
Okay.
not for media per se, but there are ways to go.
Cool. Well, thank you very much. Yeah.
8 weeks on a boat with no vegetables, but you know.
I think it'd be fun. 8 weeks, you say? Okay.
It's pretty fun, actually. Well, I had an office with Demian, so you know.
I'm going to throw up our this slide here, just so that you've all got, and for the recording as well, so that you've all got our contact details. At UT Geophysics is the link to our social media accounts, and at this link, I've got it's nothing big. It's just a series of stories and articles about anything we've done about earthquakes or people who work with earthquake research. Thank you all very much for joining. I think I'll pass over to Hope now.
Yes, great discussion. Thank you, everyone, for making the time today. This concludes our media roundtable. Our next event is a press briefing, NASA's Juno mission to Jupiter, which will begin tomorrow at 11 a.m. Central Time. Thank you all so much.
Thanks, everyone.
Thank you.
Hi.
Thank you.